Somebody should pray. Let's start.
In Jesus' name. Well, thank you for today. Thank you for strength. Oh, pray, Lord, that we begin this fast, begin the course of the way. Grant us understanding as we teach, and grant our lecturers strength as we teach us in the way. Thank you, Holy Spirit, for in Jesus' next name we pray.
Okay. So I'll be taking the, as you all know, this is CL 520 robotics and automation. So Dr. Oak is going to be taking the automation part, while I'll be taking the robotics part. So he told me that I should tell you that next week is your test one. So you people should prepare for that. So I will start with with the lecture for today. So you already have some background information of what robots are and the types of robots that are available. Even the background you have in automation, the one that Dr. Oak took for you. So just to give you just a brief recap. So there are different types of robots that are available. So we have number one says the manufacturing robots. So like you all know, robots are used to manufacture different types of things like cars, vehicles, and a lot of complex things. So we also have, so this is the classification of robots according to what it does, that's manufacturing. So we have other classification of robots according to the structure of the robot. So we have something called arm-type robots. So arm-type robots are simply robots that are in the form of the arm. So they basically look like the arm. So examples are, if I was to give you an example of an arm-type robot, like the image here is an arm-type robot. So basically, it has two links. So our arm has like two links. So that's why this kind of robot is called the arm-type robot. So they are basically the robots that are in the form or structure of the arm. Then we have mobile robots. So mobile robots are robots that, for the arm-type robots, the arm-type robots are stationary, they are fixed. So if you look at this picture, this arm-type robot is just fixed in one place. Like it cannot move around from one place to the other. So it uses its arm for reach. So it doesn't move. So it's not mobile. So it's called the arm-type robot. But mobile robots are robots that they can actually move from one place to the other. So they can transport themselves. They are not like fixed in one location like the arm-type robots. So then another classification of robots according to its structure is the humanoid robot. So as the name implies, humanoid robots are robots that are what? Yes, yes. So they are like in the structure of a human being. So this Baxter robot, though it's not shown clearly, the name is Baxter. So it's a humanoid robot. So so the other types of humanoid robot. So this is a humanoid robot. So it's in the form of a human being. So it looks like a human being. So that's why it's called the humanoid robot. So this one also is also a humanoid robot. So they are the kinds of robot that their structure is in form of a human being. So those are the three, the arm-type, the mobile, and the humanoid robots. They are basically robots that are based on structure. So the other kinds of robot that is based on function, apart from manufacturing, are the field and service robots. So field and service robots are basically robots that work in the outdoor environment. So they are allowed to just go out in the unstructured environment, and they are allowed to explore the um, the surroundings. So one example of a field and service robot is the Mars rover. So this is a Mars rover. So these kinds of robots, they are sent to the Mars, um, to the space to explore, so that they can know like what's actually going on in this in the outside world, which is not on the earth. So this is an example of a uh, field and service robots. So they are just the kind of robots that are allowed to just go out and explore the surroundings to just know what is available there. So they work in unstructured environments. Then we have tele-robots. So basically tele-robots are robots that they can be tele-operated, so they can be operated remotely. So for instance, so one example I will give of a tele robot is in the field of in the field of surgery, medical surgery. So for instance, maybe you have a doctor in um, that is not here in Nigeria, probably is based in Europe, and is performing surgery on a dummy person. So probably the surgeon cannot actually come here in Nigeria to perform the surgery. So what they will use is a tele-robot. So as the surgeon is operating on the dummy, wherever he is actually doing the operation on a live human being here in Nigeria. So those are uh, tele robots. They are tele-operated, so remotely operated, and they work on the principle of master-slave relationship. So the master uh, is the is the dummy, is the surgeon that is actually working on the dummy, while the slave is the movement that is the surgeon is performing on the dummy is translated into the slave, which is the um, person that is being operated on. So those are the types of robots that are available. So what are robots used for? So in automation, you've actually done something similar. So robots are used for highly specialized jobs. So jobs that are really very like complicated. So human beings um, cannot really grasp the nature of the complication. So you use robots to achieve jobs that are highly specialized. Then you use robots for increased productivity. That's because robots, they do things really faster. So for increased productivity. So when you use a robot, so if uh, just a person, probably can do the job in maybe 1 hour. A robot can actually finish that job in probably 1 minute. So your productivity is increased. So robots are used for improved quality jobs, because the way talking about finishing, so if a human being like does something, and for instance, in the construction of a table, like if it's a human being that is actually like hurting the table, like it's not going to be as fine as when it's a robot that is doing it, because it's kind of like a computer. So it's used for high precision jobs, because we human beings, we are not really very precise. Our precision is limited. So we use robots if you want to uh, do a very neat job. Then it's used for dangerous jobs, like for instance, in nuclear power plants, where anybody that works there is likely to be exposed to radiation. So nuclear radiation. So instead of putting human beings there, that obviously the chemicals being emitted is dangerous. Instead of putting human beings there, we put robots there, because robots can, they are not like, they cannot fall sick. So they can be in dangerous environments and do what they are supposed to do. So robots are also used for dirty jobs. So jobs that are not, they are not really very, they are not very clean. So especially in developed countries, they use robots for dirty jobs, because nobody will want to work in a place that is dirty. And given that the job is really dirty, they, yeah, the company will have to pay the person that is working there a huge amount of money. So why not just put a robot there that can just do that dirty job? Then also for repetitive tasks, we use robots for repetitive tasks. So we human beings, anytime we are doing something repeatedly, we get bored, and we just lose focus. So for instance, I think simply means that the robot should be able to, so sensing simply means that the robot should be able to um, okay, sensing simply means that the robot should be able um, to have an understanding of what the environment is all about. Like for instance, uh, if there's a mobile robot, and you know the mobile robot, it can only move. So if you have a robot that can only move and it cannot sense, so probably I'm the robot and I'm moving, but I cannot sense, I don't know that this table is in front of me, so obviously I'm going to crash into the table. So that's why a robot should have the ability to know, to sense the environment. So what is happening in my environment? Where are objects located in the environment? So you should have that capacity to sense. So another characteristic of what a robot should have is that robot should be able to plan or to control. It should be controlled, because that's like a fundamental aspect of a robot. Because if you cannot, for it to, if you just say that a robot should be able to move and it's just moving about aimlessly, you didn't actually program a task for it to do, you are not actually controlling it, then obviously you are just wasting your time. So you should be able to control it, so that it's going to work towards that plan to achieve the task it wants to do. So another key feature is that there should be a task or a goal. So I've mentioned it in the previous, in the third bullet point. So in the third bullet point, I said that it should be controlled, like it shouldn't like wander about aimlessly. So based on that control, you are giving it a set of tasks to do, a goal. And for instance, if I if I program, if I am if I have a robot and I tell the robot, the first thing is that the robot should have a goal. So probably I want the robot to move from where I am to the door. So that's the goal. That's my objective. Then based on the second or the third on this third one, which is control, then I should be able to control it such that it successfully moves from where it is to the particular goal point. So uh, that's the that's that about the task and goal. Then obviously a robot is a machine because it's not a human being. So these 5 bullet points, they are the they are the characteristics or they are the basic function of a robot. So based on these 5 bullet points, we need to give a definition of what is a robot. So I'm asking a question. So based on these 5 features which I've described, can somebody give a definition? So the definition should have all these 5 things embedded in it. So what is a robot? Okay. I didn't waste no time. Yes. You said just sense.
So, essentially, the robot is a machine that should be able to act on what it can sense from its environment according to a particular plan. All that is actually a particular
So basically, so what is said is actually the right thing. So when you are actually defining a robot, just make sure that all these key bullet points are there. But the way I defined my own robot, I said that a robot is a goal-oriented machine that can sense, plan, and act. So all of those key definitions, all of those key keywords, they are embedded inside. So you can define robots any how you want to define it, but make sure that this key definition, goal should be there, a machine should be there, sense should be able to plan, then should be then act. So those are the key definitions of what a robot should be. So we are going to so that's just a brief definition um, of robotics. So it was very brief because you guys have done automation. So automation is like some of the key concepts you've already learned. You've already learned it in automation. So we are going into configuration space. So uh, that's the that's the topic, the main topic of this lecture. So we'll be talking about configuration space, degree of freedom, then links, then open chain mechanism, then closed chain mechanism. So these are the things we'll be discussing about. So first of all, before we actually dive um, into this topic, we need to know some key terms. So because we'll be referring to some key terms like links, then end effectors, then actuators, then robot configuration. So what's a link? So a link is just a mechanical structure that is connected together by joints. So talked about the arm-type robots. So I said the arm-type robot is like the structure of an arm. So in robotics, we we call links. So this is like a link. So this is one link, then this is the second link. So a link is just like a mechanical structure that is connected together by joints. So this is the joint. So the link is the joints that connect two links together. So we make mention of links in robotics to represent uh, the the body that is connected together by uh, joints. So that's a link. Then we also define a term called actuators. So uh, you've actually done actuation in automation. So basically, actuators are they are what delivers torque or forces to the robot, because a robot has to move. Remember when I gave you some key points the robot should have? So the first thing is that the robot should be able to move. So if it cannot move, then it's not a robot. So what actually causes the robot to move? It is the actuators. And in robotics, actuators are usually motors. So electric motors, servo motors, and stepper motors that cause a robot to move. Then we have something called the end effector. So we have a definition called the end effector. So the end effector is basically connected to the end point of a robot so that it can grasp or grip objects. That's what a end effector is meant for. So at the at the um, at the end point of the robot, there should be like a if it's an arm type robot, there should be like a tool there for the robot to be able to grasp or grip objects, because mobile robots are robots that move. So those ones they don't have end effector, they don't need end effectors. But for arm type robots that are stationary, so their work is basically to pick and place objects. So in order to do that, they need an end effector to actually manipulate the object. So that is an end effector. It's usually at the end point of a robot and is attached to the link and is used for manipulating objects. So for instance, the when we're talking about the arm type robots, I said that the arm type robot is just like in the form of our hand, a human being's hand. So for us as human beings, our end effector, what's our end effector? Yes. Yes, so our end effector are our fingers. So that's what we use for grasping, we use for gripping, and we use to manipulate objects. Then this topic is about robot configuration. So what is configuration? So configuration is a specification of all the positions of the robot. So we would talk more about that. We'll talk more about that consequently. So when actually talking about when you are talking about robot configuration, we make mention of the degrees of freedom. So this is a common term in robotics, degrees of freedom, because it is the degrees of freedom that is used to specify the configuration of the robot. For instance, like it's seen in this example, a dog. A dog just has only 1 degree of freedom because it can just rotate. So it can just rotate about an axis. So it has 1 degree of freedom. So when talking about degrees of freedom, we make mention of the planar space and the 3D space. So actually, normally, the maximum amount of degrees of freedom we have any object has is actually 6 degrees of freedom. So that's the maximum amount of freedom. So it cannot go beyond 6. But for a planar object, or when you are on a plane, the maximum amount of degrees of freedom you have is 3. So what do I mean by that? So what do I mean by that? So for instance, if I'm on a planar surface, so a planar surface is just like an horizontal surface, like the board. So the board is a planar surface, is on a plane. So while 3D is like, as I am here now, I'm in 3D, but on the board here is a planar surface. So I said that on the planar surface, the maximum degree of freedom you have is 3. So 3, you can go left and right. Then the second one is that you can up and down. Then the third one is that I can actually rotate. Like for instance, if okay, like for instance, like this, if this marker, so I said I can move like this, which is 1 degree of freedom. I can move like this, which is another degree of freedom. Then I can actually rotate because the position of this marker here is different from here. So here, like the marker is horizontal, but here is rotated, is in a rotated position. So those are the 3 degrees of freedom when you are on a planar surface. So you can move left or right, up or down, or you can actually rotate on a planar surface. But in 3D, you have 6 degrees of freedom, which I'll be discussing. So I've mentioned the configuration of a robot. So is a specification of the position of the robot. Then the degrees of freedom is used to express the configuration of the robot. Then the configuration space is an n-dimensional space containing all the possible configuration of a particular robot. So like I said a dog, it has only 1 degree of freedom because a dog can only rotate. So it can only rotate this way. So it just has 1 degree of freedom. It cannot move left or right. It cannot move up and down. It just can only rotate. So a dog has only 1 degree of freedom. Then if to say that the door wasn't connected to the hinge joint, then it would have 6 degrees of freedom. because the maximum amount of degrees of freedom we have is 6. That's in three-dimensional space. So the configuration space of I said that the door has just 1 degree of freedom, but the configuration space of the of the door is given by the angle, the range of which the door can move. So for instance, this door, what's the range of motion? By what angle? What's the maximum range? Yeah, probably, yeah. So probably 180 degrees. So it can rotate from um, 0 maybe to 180 degrees. So the maximum range of motion, starting from the minimum to the maximum, is called the configuration space or the C space of the robot. So it's the range over which the door or the robot is allowed to move. So it just has 1 degree of freedom, but that degree of freedom it can move within a particular range, so which is called the C space. So as I was saying, for a planar object, the maximum moving up and down. So the first one is moving up and down. So what's moving up and down? So I'm moving up and down. So I'm elevating and giving. So that's 1 degree of freedom. Then move left and right. That's the 2nd degree of freedom. Move forward and backward. So that's the 3rd degree of freedom. Then swivel left and right. That's jawing. So jawing simply means something like this. That's jawing. Then pitching. Pitching is simply to do like this. So that's the 5th degree of freedom. Then jump up and down. So those are the 3 for translation. Then the 3 for rotation is what this airplane is doing. So if you can watch it again, it's pitching, it's rolling, then it's yawing. So those are the 3 degrees of freedom for the rotational component. So like I said, we have 6 degrees of freedom. So 3 are translational, while 3 are rotational. So let me replay the video again. So you should know the difference between go, pitch, and yaw. So those are the 3 rotational motions. Then we also have 3 translational motions. So that's the maximum you can have. So that's the maximum you can have. That's the maximum 6 you can have. So you can either move left or right, up and down, forward or backward. Then you can roll, then you can pitch, then you can yaw. So those are the 6 maximum. Outside of that, there is no movement again. So those are the 6 maximum degrees of freedom. So I want to ask a question. So what is the degrees of freedom of a car? How many degrees of freedom a car has? Then tell me, describe the motion to me. It just has 2 degrees of freedom. So it can move front and back, then it can go. So it just has 2 degrees of freedom. So a normal car can only move forward and reverse. That's 1 degree of freedom. Then it can yaw. So a car cannot move left and right. It's the yaw motion it actually uses to when it wants to move left and right. So a car only has just 2 degrees of freedom. So it's a car, does it move in 3D space or in a planar space? Yes, it just moves in a planar space. So like you can see from an airplane, the motion of an airplane has how many degrees of freedom? No, an airplane, how many degrees of freedom does an airplane One of the movements in planar space is rotation. And what is rotation? Which means yaw. Rotation actually is the yaw it does. So a car is a planar, it moves in a planar space because it can only move, planar means it can only move on a flat horizontal space. So it moves in planar space. So I was asking, how many degrees of freedom does an airplane have? Why is it so? Why is it So I think the plane has 5 degrees of freedom. That's why I think. So you people all have your different theories, but so it can go like this, then it can move forward and backward, then the 3 rotational motion. So it can pitch, it can roll, and it can jump. So those are the 5 degrees of freedom. So we go to robot joints. So when we talked about links, I said that a link is like the mechanical structure which a joint connects together. So we are looking now into robot joints. So we have different types of joints. So the first type of joint we have is the revolute joint. So a revolute joint is a joint that can rotate. So that's a So we have different types of joints. So the first type is revolute joint. So the revolute joint is for rotation, like the door, the joint at the door. is a revolute joint. So you just when two links are connected about the joint, it's going to rotate. It's going to cause rotational motion. Then the second type of joint we have is a prismatic joint. So a prismatic joint is like a linear, is causes a linear motion. So uh, is a joint that when the joint is actuated, a linear uh, a linear motion is produced, not a rotational motion. So that's a prismatic joint. Then an helical joint is also called a screw joint. So is a kind of joint that as you are rotating it, it causes a linear motion. Like when you are screwing a nail. So as you are actually rotating it, is causing um, is causing a linear motion. So that is an as you are rotating it. So that's this is the definition. So an helical joint is a screw joint. So it allows both uh, simultaneous rotation and translation about a screw axis. So a prismatic joint is a sliding joint along the direction of the joint axis. So this is a prismatic motion. So it's linear about an axis. Then the revolute joint, this is the motion of the revolute joint. So it's rotational motion. Then for an helical joint, it's rotating, is a joint that it consists of simultaneous rotation and translation. So this is an helical joint. It's also called a screw joint. Then the types of joints that we discussed previously, the revolute, the prismatic, and the helical, they they are planar joints. So they work in a planar space. So these other types of joints, they actually work in 3D space. So three-dimensional space. So you have the cylindrical joint, the universal joint, and the spherical joint. So each of these joints, how many degrees of freedom is the revolute joint? It's just 1 degree of freedom. The prismatic joint is just 1 degree of freedom. Then the helical joint is also one degree of freedom. Then in 3D space, we have this kind of joint, the cylindrical joint. So you have to know the difference between the cylindrical joint and the helical joint. The cylindrical joint allows for simultaneous rotation and translation, while the cylindrical joint allows for independent rotation and translation. So for that helical joint, translation is the motion of translation. The motion of rotation is coupled with translation. So as it rotates, it translates. But for the cylindrical joint, it's independent. The two the two motions they work independently. So it can rotate, then it can also translate. So this is the arrow for rotation. Then this is the arrow for translation. Then a universal joint has 2 degrees of freedom. So I said as the cylindrical joint so has 2 degrees of freedom. This is the rotation component, then the translation component. So that's two. Then the universal joint also has 2 degrees of freedom. So this is one degree of freedom, and this is another degrees of freedom. So it has two revolute joints, but which are orthogonal to each other. They are 90 degrees to each other. Then the spherical joint. The spherical joint is it has 3 degrees of freedom. So it's the joint that is at our shoulder. It has 3 degrees of freedom. So can roll, pitch, and yaw. So these are the uh, 3 kinds of joints we have in um, in 3D space. So, like I said previously, the revolute joint has only 1 degree of freedom. So, by the virtue of the fact that it has 1 degree of freedom, it means that it has 2 constraints. Because I told you that for a planar, um, in a planar space, the maximum degree of freedom you have is 3. So since a revolute joint has 1 degree of freedom, so that means that it's constrained by two of its degrees of freedom is constrained. Similar to the prismatic joint, it has 1 degree of freedom. So that means that the constraints it has is 2 because it's a planar motion and the maximum you have is 3. Then for an helical joint, you also have just 1 degree of freedom for an helical joint. But an helical joint is not actually is not a planar motion. It's it rotates, then it translates. So the rotation and the translation are coupled to each other. So it's actually a 3D motion. So it's, and I told you that in 3D space, the maximum degree of freedom you have is 5. So that means that there are 5 constraints. So for a similar no, it has 1 degree of freedom. So there are 5 constraints. Because it's a 3D space, so the maximum degrees of freedom we have is 6. So since it has 1 degree of freedom, so that means it's constrained by 5 motions. Then the cylindrical joint has 2 degrees of freedom. That means it's constrained by 4. Also, the universal joint has 2 revolutes, 2 revolutes, and it's just 2 revolute joints orthogonal to each other. So it has 4 constraints. Then the spherical joint has 3 degrees of freedom. So it has 3 constraints. So we are going to be calculating the degrees of freedom of a robot. So this is the formula that is used to calculate the degrees of freedom for any particular robot. So you can write it in your notes because we are going to be using it to I'm going to be using it to do some calculations to calculate the degrees of freedom in a particular robot. So this is called the Grubler formula. Grubler formula. Grubler formula. So it's a formula that is used to calculate the number of degrees of freedom of any robot or for any object. So n is the number of links. So we talked about links. So like if this is a robot, this is a link, this is a link. So those are just links. So n is equal to the number of links the robot has. Then n sorry. N is equal to the number of links. So it's n that is equal to the number of links, not n. Then n M is the number of degrees of freedom. Like for a planar object, M is equal to 3. That's for a planar motion or for a planar object. Then for a 3D object, M is equal to 6. So M is the maximum number of degrees of freedom, given that it's either a planar object or a 3D object. So that's M. Then J is the number of joints. So this is the joint. So you count the number of joints the particular robot has. So this is the number of joints. Then F is the number of degrees of freedom for each particular joint. So we're going to use an example so that you understand what this term actually means. So it's the number of degrees of freedom for a particular joint. So you count the number of joints. So each joint should have a degree of freedom, given that AB is. So if the joint is revolute, that means it has 1 degree of freedom. F is equal to 1. If it's prismatic, F is also equal to 1. So if it's helical, F is equal to 1. If it's cylindrical, F is equal to 2. If it's universal, F is equal to 2. Then if it's spherical, F is equal to 3. So that's what F signifies. So before we actually use this formula, we have to distinguish between two kinds of mechanisms: the open chain mechanism and the closed chain mechanism. So basically, the closed chain mechanism is a mechanism that has a closed loop. So when you look at it, it forms a closed loop. So the example that is given in the board said the person standing with his feet on the ground is an example of a closed chain mechanism, because the closed loop. So if this is the person that is actually standing on the ground, so we call this a closed chain mechanism, because the link, it starts from here, then it goes here, then it goes to the other leg, then to the ground. So it's actually closed. So that's why we say it's a closed mechanism. It's a closed chain mechanism. So it's any mechanism that has a closed loop. Then an open chain mechanism or a serial mechanism is a mechanism that doesn't form a closed loop. For instance, when your arm is allowed to move freely in space, so it's not connected to the ground. So it's like an open chain mechanism. So before we actually start doing the calculation, let's look at this formula. So N is the number of links, where the graph is also referred to as a link. So when you are counting the number of links, you have to add +1 to it, because the ground is also referred to as a link. So you should note that. So let's do some examples. Okay, so let's do this example. So this example is a 4-bar linkage. So and we're told that is planar. So this is very important. So since that we are told that this is a planar object, so it means that our M is what? 3. It means that our M is 3. So that's what it means. Then looking at this particular robot, is this Is it a closed chain mechanism or an open chain mechanism? Yes, it's a closed chain mechanism. So our aim is to calculate the number of degrees of freedom of this particular robot. So given that it's a planar object, n is equal to 3. So you have 3 here. Then n is equal to the number of links. So it has 1, 2, 3. Then the ground is also a link. So that's 4. So that's why you have the 4 here. Minus 1. Then j is the number of joints. We have 1, 2, 3, 4. So that's why you have 4 here. Then F is the number of degrees of freedom of each joint. So each one is a revolute joint. It has 1 degree of freedom. So that's why you have 4 here. So when you use the Grubler formula, you say that this robot has just 1 degree of freedom. So let's do another example. So this is another robot. So we want to calculate its degrees of freedom. So it's a planar object. So that means that n is equal to 3. Then n is the number of joints. It has 1, 2, 3. So since the ground is also included as a joint, so n is equal to 4. So 4 minus 1. Then j is the number of joints. So it has 3 joints. Then the number of degrees of freedom of each joint is 1. So that's 3. So at the end of the day, it will give you 1 degree of freedom. So this is a 4-link planar serial chain. So can you calculate the degrees of freedom of this? So it's planar, is on a plane. So that means that M is 3. Then the number of links, 1, 2, 3, 4, with 5. So M is equal to 5. Then J, 1, 2, 3, 4, 4. Then Fi is equal to 4. Because it has 4 joints. Then each joint has 1 degree of freedom. So for your calculation, what's the number of degrees of freedom? 4. So it has 4 degrees of freedom. So can you calculate the number of degrees of freedom of this robot? So this is a planar object. So that means n is 3. Then n. So n is 3. Then n. So you be told that it is a planar object. You be told. Then n, you're not counting all of this. So it's just 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So n is 6. is the number of joints.
1, 2, 3, 4, 5, 6, 7. Joints 1, 2, 3, 4, 5, 6, 7.
Then Fi, the number of degrees of freedom is also 7. So when you do the calculation, it's the degrees of freedom it has is just 1. Then we'll do the last example. This is a Stewart ground platform. Stewart ground platform. So it's a 3D object. So it's not a planar object, it's a 3D object. Then this is how it's so this is the how it moves. So it's a planar object and it has 6 degrees of freedom. So when you really study the motion, you will see that it has 6 degrees of freedom. So it can move up and down, left and right, forward or backward, then it can roll, pitch, and yaw. And it's a 3D object. So this is it here. Yes. No. But it's the top that has to move. So the top is moving. And if I show you the circulation, the top can move. So it's moving up and down. Then it's rotating. Then it's moving left and right now. It's moving left and right now. So it can also move forward and backward. So yeah. Yes, so to count the number of things, you count this, then you count each of these. So it's 14, yes. So that's what because this last thing is already on round. So you count it, so it's 14. So n is equal to 6. Yes. It's a prismatic joint. It's a prismatic joint.
This compound joint.
The number of joints. The number of joints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, Oh, right. Yes, it has 18 joints. Yes. The number of degrees of freedom offered by each joint. Like this particular joint contains.
Sorry. What's happening in this class? The letter is telling you guys are making noise.
All the joints at the base, each of them have 2 degrees of freedom. So that this joint has 1 degree of freedom. Yeah, it is spherical joint. Yes. So for this, you have 6 times 1. So 6 times 2. That's 6 times 3. So now we are for this, the joint at the base is a universal joint. So you can see it has 2 arrows. Okay. So that means it has, each of them has 2 degrees of freedom. Then for this is a prismatic joint. So each of them has 1 degree of freedom. Then for this is a spherical joint. Each of them has 3 degrees of freedom. So that's I had to say. So when you do the maths, you are going to arrive at 6 degrees of freedom. So for your assignment is to calculate using the Grubler formula. The assignment is using the Grubler formula. Calculate the number of degrees of freedom of a human body. So human body, they are composed of limbs. So these are the limbs, thighs, the legs. So you're going to draw then you use Grubler's formula to calculate the number of degrees of freedom. The first part is without the arms, then the second one is with arms. So there's part A and part B. Yes. So we are going to be ending the class for today.
Thank you,